to sort of simulate the same structure that we see in homework 2 part 2. I'll find the Piazza post.
What is the number again?
It's 2:45. Sorry, it's 8:45.
Can you speak up? I already hear you.
Can you hear me now? Can you guys hear me now?
I can hear you.
Not really. I can hear you, but it's really low.
The mic close. Sorry.
Is it better now?
Yes.
Okay. So I'll just repeat what I said. Please find Piazza post number 845. It has both the notebook and the slides for this lab.
The slide cannot be. It requires permission. I'm logging in a CMU email, but it still says I don't have permission.
Is nobody able to access the slides?
It's restricted for CMU ID.
Okay. Is the notebook accessible? I think we can check the slides and upload it later. If the notebook is accessible, I think we can continue for now. Can someone confirm if the notebook is accessible? Okay. Okay, so this lab is similar to your homework 2P2, the same face classification and verification problem. The first part of it is face classification. So this is basically like an image recognition problem, similar to your homework 2P2, where you have around 8,000 different categories of faces. And we are going to simulate the same thing, but for a smaller data set. And we'll see how we can use CMUs to identify different features in the images, like your eyes, your nose, and find different patterns that are similar to one single category. And we can see how we can make the CNN learn all these features and categorize them. The second part is the face verification part. So this is kind of a tricky part because you'll be using the same data set and the same features that we learned to make the model verify if two data points from the data set are of the same class. So this is usually achieved by comparing some of the features between the two faces. So we'll have some sort of face embeddings that we create from the data set, and we'll have a similarity score comparison between the embeddings, and we'll see how close to each other they are in a plane to identify if they are of the same class. So this can be used for like your face ID for like your camera recognition or like attendance systems and stuff. So how do you compare two face features? You basically calculate the distance between the face embeddings in the uh, 2D plane, and the distance between these embeddings should be low, while the cosine similarity between them should be high. So if the two vectors are along the same direction, then the cosine similarity will be high, whereas if they're orthogonal, it will be 0, and if they are pointing to two different opposite directions, it will be low. So this is exactly what we're trying to simulate in this lab today. So I'm gonna give you guys a few seconds to set up your notebook, and please identify the Piazza post and make a copy of the notebook so that we can run these experiments in parallel. And as we move from one checkpoint to other, please mark the checkpoint as done in the checkpoint poll post. So the first checkpoint is basically making a copy of the notebook in your drive. So if you're done, please answer the poll on Piazza and we can move forward. So I hope you guys have made a copy of the notebook. Moving forward. So what is the difference between classification and verification? So in face classification, you're given an image and you're identifying which class or who this person is. For example, it can be any X, Y, or Z, and this is used in applications like attendance systems. You're basically making the model learn different features that are similar to one particular class, like the eye position, your nose, your lips, your ears, etc. And it's a pattern recognition problem, and you're letting the CNN model learn what features correlate to each other, and you're classifying it based on which class it is. Whereas in face verification, you're given a pair of images of the same person, and you have to verify if the features correlate to the same class. So in this problem, we're going to use the same data set to do both the classification and the verification problem. So the face verification can be used to like unlock your smartphone and other similar applications. Moving on to checkpoint 2 is you're checking if you have a GPU. This is just NVIDIA SMI. I'll give you guys a couple of minutes to do this. I hope you guys are done with checkpoint 2. Moving on, these are just the imports that we need for the lab. And checkpoint 3 is sort of the stuff that we did in the previous lab, a reminder of what 2D convolution is. So we have an image in NumPy array here, a kernel, and we are trying to make a 2D convolution feature map of stride 1 and padding 1. So here, if the padding is set to 0, we're setting the padding to 1 if it's greater than 0. And you're, the 2D convolution, you're basically sliding the kernel on top of the image NumPy array. So why do we need padding? Does anyone remember why we need padding?
Preserve the dimensions.
Yeah, and also to make sure that your corner edge features are also extracted. So here you're basically calculating the output dimensions using the stride that you're given, and you're initializing the output feature map, and you're performing the convolution operations on the output height and the output width, and you're calculating the region of interest, and you're outputting the NumPy sum of the region into the kernel. So for this particular NumPy array and this particular kernel, the left topmost features will be more highlighted as opposed to the right bottommost corner features. So this is how your feature map would look like. This is basically checkpoint number 3. moving on to checkpoint 4. So the dataset that we're using today is the LFW people dataset. It's similar to the dataset that we have in homework 2 part 2, except lesser number of images. So this dataset has face images of, I think, around 50 categories. So we are loading the dataset from the library, and the X is the images and Y is the target label of the LFW dataset. So checkpoint number 4 is you have to print the number of classes in the LFW dataset. I'll give you guys some time to finish checkpoint number 4. So this is just, you have to print the length of the target names variable. I hope you guys are done. Can we move on? So moving on to the next cell, we are just plotting some sample images from the LFW dataset. You can see the diversity of the classes in the images here. And then we are pre-processing the train and the test split. So in order for the CNN to learn the features, we are first normalizing the images. So here, this would be like a feature vector between 0 to 255, and you're normalizing it by dividing it to 255. And then you're adding another dimension, because CNN would take 3 like RGB images, and so you're adding another channel to it. And you're one hot encoding the labels here. So the label vectors of the LFW is just the class to which each image belongs to. You're applying one hot encoding to the labels, and you're splitting the training and the test data set. We are giving a test site of 0.2 here, which means it's a split of 80 is to 20. And we are printing the training sample and the test sample size. So we have a training sample of around 1,250 images and a test sample of around 300 images in the LFW dataset. the next cell block, we are applying data augmentation techniques to the data set. Since the LFW data set only has 1,300 training samples, we want to increase the number of images that we want the CNN model to see. So we are applying a couple of augmentation techniques here. The first one is the rotation range, and we're setting it to 15, which means that it will randomly rotate the images to either plus or minus 15 for the training sample set. The width shift range, we are setting it to 0.1, which means it will be flipped, the width will be shift to 10% randomly to the training set. Similarly, we are shifting the height of the images, which will also be changed to 10% randomly. And we are also including horizontal flip. So some of the images will be flipped in the training sample set, and we are setting a zoom range of 0.1, which will also randomly set a zoom to the training sample set. So we are applying the augmentation techniques only to the training set and not the test set, because we want the test set to be fairly evaluated here. I'll pause here again for you guys to finish up these two code sets. Moving on to checkpoint number 5, we are building the CNN model here. So here we have 3 convolutional layers, followed by an activation of ReLU for each layer, 2D max pooling layer after each convolution layer, and finally a flattening layer. And we are also getting the embedding output, and we're naming it embeddings. We will use the same output layer later when we are doing the verification module. And finally, we are applying a dropout layer of 0.5. And the output is we are adding a dense layer with softmax activation to get the output logics. So here they've just expanded what each convolutional block is. And in the end, we are just printing the model summary. This is your checkpoint number 4. Please finish up the polls on Piazza as you're doing all the checkpoints.
understand in the CNN why we have none as one of the dimensions.
Which part?
The output shape,
Yeah.
why is there none in the,
This one?
no, like in the output shape? Yeah, like the column output shape. Why is the first dimension none?
Uh, so it should be 3 dimensions. Okay, that is the batch size. When you're setting the batch size, then it will take the number of it. So here 50 is the height, 37 is the width, and 1 is the channel size. None is the batch size. Moving on to checkpoint number 6. Here we are training the model. We are using Adam as an optimizer, and we are using cross entropy loss function. We are saving the checkpoint of the model just similar to how you track it on MonDB. And we're just training it for 45 epochs here, but you guys are free to experiment and try other optimizers, loss functions, and you can also play with different metrics here. I hope you guys are done with checkpoint number 6. If we can move on. So yeah, the final part of this lab is the verification part. So remember how we defined the embedding layer when we were building the model? We're going to use the same embedding layer to define an embedding model, and we're going to get generate sample embeddings for like 10 of the samples from our test set. And we're going to predict what how these embeddings look like, and we're going to predict what the cosine similarity is between these embeddings, and we're going to see if they are of the same class or not. So the seventh checkpoint is basically creating the embeddings for these sample sets. I'll pause here again for you guys to finish this. So cosine similarity is one of the ways in which we can do verification, whereas in your homework, you can try other different metrics as well. There's also different kinds of losses that you can use, like contrastive losses, arc phase, sphere phase, etc. It's pretty elaborate in the write-up. So moving on to the final checkpoint, checkpoint number 8. So we are just calculating the cosine similarity between the two embeddings that we've defined here. And we are setting a threshold of 0.75. You can alter this threshold and play around with different values if you want, based on what your output and the data set that you have. So if the cosine similarity is higher, it means that the two data points are of the same category. So which is what we are trying to verify here. So this is checkpoint number 8. You're free to change the value of the threshold and experiment with new things. So that was the last checkpoint. So lab 6 was basically a very high level simulation of homework 2P2 for you guys. But to reach the high level cutoff, you definitely have to experiment with a lot of things. You have to experiment with different schedulers, optimizers, different architectures. And I definitely recommend using the loss functions given in the write-up, specifically the different contrast losses, arc phase, triplet, margin loss, etc., to reach the high cutoff. And also make sure that you're applying a couple of the augmentation techniques as well. Uh, and experiment with a lot of different hyperparameters, run different ablations within your study group so that you can reach the high cutoff on time. So yeah, this is lab 6. Thank you. I'll be here if you have any doubts and questions about homework 2.